Welcome back, dear friends, to the thrilling world of inverter-based resources. In our last episode, we dove deep into the realm of momentary cessation, uncovering its mysteries, and learning how it affects these incredible power sources. Today, get ready for another electrifying adventure, as we explore a new challenge, the enigma of frequency measurement-related tripping. Imagine this, the grid-connected inverter-based resource humming along, delivering power with precision. But suddenly, without warning, it trips. But wait. The frequency is within the acceptable limits. So why is this happening? Join us on this captivating journey as we unravel this puzzling phenomenon. During this session, we'll delve into the heart of the matter, exploring the underlying reasons why inverter-based resources face frequency-related tripping, even when the frequencies are seemingly well-behaved. But fear not. We won't leave you hanging. We're not just here to highlight the problem, we're here to discuss solutions. Through clear and concise explanations, we will present you through the intricacies of this issue. You'll discover the secrets behind mitigating these challenges, including the introduction of frequency ride-through characteristics. It's time to arm yourself with knowledge and equip yourself with the tools to overcome these obstacles. So, fasten your seatbelts and get ready for an exhilarating ride. Before we dive into the fascinating world of frequency-related tripping in IBR, let's take a moment to understand the concept of frequency itself. In the realm of electrical signals, frequency refers to the rate at which a cyclic signal repeats itself within a given time frame. It's like the heartbeat of the power system, dictating the rhythm at which energy flows. In power systems, the steady-state waveforms of voltage and current follow a sinusoidal pattern, gracefully oscillating back and forth. These waveforms repeat themselves a specific number of times every second, and this repetition defines the frequency of the system. Typically, power systems around the world operate at a nominal frequency of either 50 or 60 Hz, depending on the region. This means that the sinusoidal waveforms complete a full cycle 50 or 60 times per second. But here's where it gets interesting. Despite having a nominal frequency, the actual frequency of a power system is never constant. It fluctuates and varies continuously, much like the ebb and flow of tides. This constant variation in frequency is a direct result of the delicate balance between power generation and load demand within the system. As the load increases or decreases, the frequency adjusts accordingly, striving to maintain equilibrium. In essence, the frequency of a power system is a reflection of its health and balance. When the load and generation are perfectly aligned, the frequency remains stable. However, any significant imbalance can cause fluctuations, which may lead to issues like frequency-related tripping. Now that we have a solid foundation of understanding frequency and its relationship with power systems, we're ready to explore the captivating world of frequency-related tripping and IBR. Why are frequency-related tripping mechanisms enabled in power systems? Let's delve into the crucial reasons behind this important safety feature. Conventional generators, with their large rotating masses, are meticulously designed to operate at the rated frequency, with minor variations within a specified range for a limited duration. This range ensures their optimal performance and protects them from physical damage. To preserve the integrity of these generators, high-frequency and low-frequency trip settings are implemented. These settings act as protective measures, preventing the generators from operating outside their safe frequency range. By tripping the generators in case of excessive frequency deviations, the system avoids potential damage to these critical components. But it doesn't stop there. Transformers, vital components of the power system, are also rated to operate at specific frequencies. As the frequency deviates from the nominal value, the impedance of transformers changes. This can lead to capacity limitations and even cause damage to these essential devices. To mitigate these risks, overflux relays, triggered by voltage and frequency deviations, are employed to protect transformers. These relays act as guardians, ensuring that the transformers operate within their design limits and preventing potential harm due to excessive frequency variations. Considering the detrimental effects of significant frequency variations on the power system, various safety measures are in place. Some grids implement stage-wise generator and load tripping mechanisms, designed to control high-frequency and low-frequency deviations respectively. These measures help maintain system stability and protect both the generators and the interconnected equipment. By setting limits and enabling frequency-related tripping, power systems with synchronous generators can better safeguard against significant frequency variations. These protective measures ensure the reliability and longevity of the power system, preventing potential damage and disruptions. Let's explore the consequences that can arise when frequency-based safety mechanisms are absent from a power system. To illustrate this, we'll take a closer look at the scenario involving a windmill without any mechanism to control its operation during high wind speeds. Imagine a windmill harnessing the power of the wind, spinning with tremendous speed. Without a wind speed-based safety mechanism, it continues to operate unchecked, oblivious to the risks that lie ahead. As the wind speed continues to rise, the windmill reaches its operational limits. Without the ability to sense the wind speed, frequency deviations and adjusting its blade direction to avoid such speed, it fails to adjust its operation accordingly. In this uncontrolled state, the windmill is unable to match its rotational speed to the changing wind conditions. The excessive rotational speed can lead to structural stress and mechanical failures, putting the windmill at risk. Without the protective mechanism in place, the windmill becomes vulnerable to damage, potentially leading to catastrophic consequences. This scenario highlights the importance of frequency-based safety mechanisms in power systems. Let's take an example of United States where NERC has PRC024 criteria for generator frequency and voltage protective relay settings. This standard defines the allowable frequency range in which generators can operate continuously and the thresholds beyond which they are designed to trip. In the Eastern Interconnection, generators are permitted to operate continuously within a frequency range of 57.8 to 61.8 Hz. However, if the frequency exceeds 61.8 Hz or falls below 57.8 Hz, instantaneous trip settings are activated, ensuring a swift response to abnormal frequency deviations. Similar are ranges for West Quebec and ERCOT interconnection. It was observed that inverter-based resources, IBRs, trip on instantaneous frequency protection during faults, while other synchronous generators remain unaffected. The investigation that followed shed light on a surprising discovery. Picture a bustling power system control room, where vigilant operators monitor the grid stability. During a fault event, system operators were taken aback when IBRs trip on instantaneous frequency protection, unlike their synchronous generator counterparts. Confusion filled the room as they wondered why the IBRs were responding differently to the fault conditions. It was evident that something peculiar was happening. A comprehensive analysis was conducted to uncover the underlying cause. It was soon realized that during transient conditions, the frequency measurements recorded by the IBRs were not accurate. Transients, characterized by rapid changes in the power system's behavior, can introduce complexities in frequency measurements. In the case of IBRs, these transients were distorting the frequency measurements, leading to incorrect values being recorded. As a result, the faulty frequency measurements triggered the instantaneous frequency protection of the IBRs, causing them to trip even though the fault was not severe enough to warrant such a response from other synchronous generators. This highlighted the importance of robust frequency measurement. In response to the frequency-based tripping observed in inverter-based resources during faults, a series of remedial measures implementation can help in ensuring accurate frequency measurements and reliable protection. Let's explore these measures in detail. One of the key aspects that should be addressed is the duration of frequency measurements. It is recognized that calculating frequency over a specific window of time provides more accurate results while filtering out noise and transient variations. Typical window lengths range from 3 to 6 cycles, which translates to approximately 60 to 120 milliseconds in a 50 Hz power system. By utilizing this windowed approach, the frequency measurements become more robust and reliable. However, it is crucial to distinguish between instantaneous frequency calculation and frequency measurements used for protection purposes. The instantaneous frequency, calculated at a single moment, may not accurately represent the system's overall behavior during transients or faults. To address this, it is recommended not to rely on instantaneous calculated frequency for protection purposes. Instead, protection schemes are modified to utilize frequency calculations over the specified window of 3 to 6 cycles. By incorporating this approach, the protection systems become more responsive to true frequency deviations and mitigate the risk of false tripping or inadequate response during fault events. Inverter-based resources present a unique advantage in the power system. Unlike conventional generators, they do not involve an electromechanical system and are not directly impacted by grid frequency variations. This characteristic eliminates the risk of direct damage to IBRs from high or low frequencies. Recognizing this distinction, efforts will help to optimize the protection schemes for IBRs and avoid erroneous tripping during frequency deviations. One effective approach was the incorporation of suitable time delays in the frequency-based tripping mechanisms for IBRs. By introducing these time delays, the protection systems allow for a more comprehensive evaluation of the frequency conditions before triggering a trip event. This prevents unnecessary tripping in cases where the frequency deviation is transient or within acceptable limits. The purpose of these time delays is to provide a buffer period during which the system can stabilize or recover from temporary frequency fluctuations without triggering a false trip. The duration of these time delays is carefully determined based on the specific characteristics of the IBRs and the overall system dynamics. It ensures that the protection scheme remains responsive to genuine frequency anomalies while avoiding unnecessary disruption to the operation of IBRs. Through the implementation of suitable time delays, the industry has significantly reduced the occurrence of erroneous tripping in IBRs, further enhancing their reliability and operational efficiency. Another method is the implementation of low-voltage inhibit for frequency protection relays, which plays a crucial role in safeguarding both synchronous machines and inverter-based resource. Let's delve into the details. Synchronous machines, equipped with under- and over-frequency protection functions, utilize Relay 81 to monitor and respond to frequency deviations. However, in the presence of low-voltage conditions, a unique feature known as low-voltage inhibit comes into play. The low-voltage inhibit function ensures that the frequency protection relay becomes disabled when the voltage falls below a certain cutoff level. The primary intent behind this cutoff is to avoid the challenges associated with accurately calculating frequency during fault conditions or substantial voltage dips. By inhibiting the relay during low-voltage situations, the system mitigates the possibility of incorrect frequency measurements, thereby ensuring more accurate and reliable fault detection and protection. This approach is not exclusive to synchronous machines alone. In modern power systems, where digital relays are prevalent, similar techniques can be extended to inverter-based resources as well. Applying the low-voltage inhibit concept to IBRs allows for the inhibition of frequency tripping during and immediately after low-voltage conditions, aligning them with the practices employed for synchronous machines. However, it's important to note that the decision to implement low-voltage inhibit is contingent upon the tolerance levels of the equipment in question. Each piece of equipment, whether it be a synchronous machine or an inverter-based resource, has its own specified tolerance levels for voltage variations. These levels serve as the deciding factor in determining whether low-voltage inhibit is necessary and appropriate. By carefully assessing the equipment's tolerance levels and implementing the low-voltage inhibit function where required, power system operators and engineers ensure optimal protection and reliable operation for synchronous machines and inverter-based resources alike. While IBRs are generally more resilient to frequency variations, there are certain factors that need to be taken into account. One important consideration is the impact on the AC filtering within the inverter itself. Large frequency fluctuations can affect the performance and effectiveness of the AC filtering system, potentially leading to issues or inefficiencies. Additionally, AC transformers in IBR plants may be susceptible to saturation due to frequency variations. This saturation can affect the overall performance and capacity of the IBR plant. Moreover, other transformers and control components within the IBR plant system may also have limitations and constraints related to frequency variations. To address these concerns, existing inverter-based resources have been designed based on existing standards and equipment specifications. These specifications guide the determination of frequency trip settings and ensure that the equipment operates within safe and optimal parameters. The equipment specifications of the facility, including the inverter and its control systems, should be the guiding factor in determining the need for frequency trips. For existing IBRs, it is recommended to expand the frequency trip setting limits to avoid unwanted trips to the extent possible. This allows the resources to operate within a wider range of frequencies, accommodating minor fluctuations without unnecessary interruptions. On the other hand, new IBRs should be designed with a wide frequency ride-through range in mind from the outset. By incorporating this wider range into their specifications, new IBRs can better adapt to the dynamic nature of the power system and ensure reliable operation even during significant frequency variations. By aligning the frequency trip settings with the equipment specifications, both existing and new inverter-based resources can operate within their intended performance range, minimizing the risk of unwanted trips and optimizing system efficiency. In the dynamic world of power system standards, continuous advancements pave the way for a more seamless integration of inverter-based resources. One such milestone is the publication of the IEEE 2800 standard for IBRs in 2022, providing well-defined frequency ride-through characteristics. This new standard marks a shifting of IBR from the previously used IEEE 1547 standard, which is for distributed energy resources, published in 2018. The frequency ride-through characteristic outlined in the IEEE 2800 standard specifically addresses the unique requirements and considerations of IBRs. By complying with the IEEE 2800 standard, IBRs can ensure that frequency-related tripping events become a thing of the past. This harmonization of practices and guidelines sets the stage for a more reliable and resilient power system. As more IBRs align themselves with the IEEE 2800 standard, the power system gains increased stability and resilience, bolstered by the seamless integration of these resources into the grid. With each step forward in standardization and harmonization, we move closer to a power system that fully embraces the potential of inverter-based resources, while ensuring their compatibility and reliability within the broader energy landscape. Stay tuned to our YouTube channel for more exciting developments and updates as the world of power systems continues to evolve. Until next time, keep exploring, keep innovating, and keep powering the world. Do not forget to like, subscribe and share.